Hey there, and welcome to this explainer. Today we're tackling one of the most fascinating challenges in all of science. We're going to figure out how to take the completely invisible world of atoms and molecules and translate it into tangible physical things we can actually measure in a lab. I mean, it sounds like magic, but as you'll see, it's just incredibly clever chemistry.
So think about a massive sack of rice. You don't sit there and count every single grain, right? No way. That would literally take a lifetime. Instead, you measure the rice by weight or by volume. You're basically using a measurable macro-scale unit to represent a massive quantity of tiny individual items.
Which brings us to a really crucial question. Do you think we can count the number of atoms in a substance the exact same way we count those rice grains in a sack? Atoms are exponentially smaller than rice grains. They're so unbelievably tiny that counting them one by one is literally impossible. And yet, to pull off any chemical reaction accurately, chemists need to know exactly how many atoms they're mixing together. So how do they solve this? Well, the answer pretty much changes everything.
Okay, let's dive right into this. Here's our roadmap for today. 1. Counting the invisible. 2. Meet the mole. 3. Gases and molar volume. 4. Stoichiometry and limiting reactants. 5. Concentration and titration. And finally, 6. Formulas, yield, and purity.
Section 1. Counting the invisible. Mastering the baseline vocabulary.
Right, before we can even think about doing chemical calculations, we need to lay down some foundational terms. These allow us to actually compare the masses of different atoms. Let's start with relative atomic mass, which you'll see represented by the symbol Ar. This is the average mass of the isotopes of an element compared to exactly 1/12 of the mass of a carbon-12 atom. You might be wondering, why carbon-12? Well, it's just the agreed-upon benchmark in the chemistry world. But the absolutely crucial thing to remember here is that this is a relative comparison. It is just a ratio. And because it's a ratio, it has absolutely no units. You won't see grams or ounces here, literally just a number.
And once you know the relative atomic mass of individual atoms, you can easily find the relative molecular mass, or MR. This one is super straightforward. It's simply the sum of all the relative atomic masses of the elements making up a molecule. You literally just add them together. And again, it's a ratio, so there's zero unit attached. A quick aside though, if you're dealing with an ionic compound, say sodium chloride, which doesn't form discrete molecules, you're doing the exact same math, but you just call it the relative formula mass instead.
Section 2. Meet the mole, the chemist's ultimate translation device.
So, now that we know how atoms compare to one another in mass, it's time to introduce the real hero of our explainer. What exactly is the mole? Represented by the symbol MOL. The mole is the standard unit of amount of substance. And get ready, because here is the magic number. 1 mole of any substance contains exactly 6.02 times 10 to the 23rd power particles. This absolutely staggering number is known as the Avogadro constant. You can kind of think of it like a chemist's dozen. Just like a dozen always means 12, whether you're talking about eggs or donuts, a mole always means 6.02 times 10 to the 23rd power, whether you're talking about atoms, molecules, or ions. To put that into perspective for you, a single mole of donuts would cover the entire surface of the Earth, literally miles deep.
Now, what's really interesting is how beautifully everything connects here. The molar mass, which is just the mass of 1 mole of a substance in grams, perfectly mirrors its relative mass. Carbon has a relative atomic mass of 12, so 1 mole of carbon weighs exactly 12 grams. Water has a relative molecular mass of 18, so 1 mole of water weighs exactly 18 grams. It's a perfect match. This is exactly how chemists translate that invisible relative mass of an atom into tangible grams that they can physically weigh on a lab scale.
Section 3. Gases and molar volume. Measuring the invisible spaces.
But hey, what happens when we aren't dealing with neat little powders and liquids that we can just plop onto a scale? Measuring the mass of a floating, invisible gas is definitely a bit trickier. Thankfully, gases play by very strict rules when it comes to volume. At room temperature and pressure, 1 mole of literally any gas occupies exactly 24 cubic decimeters, which, for the record, is 24,000 cubic centimeters. And it really doesn't matter if it's heavy oxygen gas or super light hydrogen gas. 1 mole of it will always puff out to fill that exact same volume, every single time.
Let's visualize that. Imagine 2 balloons of the exact same volume, sitting at the exact same temperature and pressure. They are going to contain the exact same number of gaseous particles. Period. No exceptions. However, if you have 2 balloons that have the exact same mass, let's say they both weigh exactly 10 grams, but they're filled with different gases, They will absolutely not contain the same number of particles, and they're going to be completely different sizes. So, volume, not mass, is your ultimate shortcut to counting gas particles.
Section 4. Stoichiometry and limiting reactants. Scaling up to chemical reactions.
Okay, so now that we have our baseline unit, let's start actually mixing things together. Stoichiometry. It's a big, intimidating word, but it's really just the relationship between the moles of reactants you put into a reaction and the moles of products you get out. Now, in a perfect world, you'd mix exact amounts of chemicals and they'd all perfectly, completely transform. But in the real world, one chemical usually runs out first. We call this the limiting reactant. It's the reactant that gets completely used up, and it single-handedly dictates the final amount of product formed. Think about baking a cake. If you have 10 boxes of cake mix, but you only have 2 eggs in the fridge, it doesn't matter how much mix you have. Those eggs are your limiting reactant. Once they're gone, the baking completely stops. And it's the exact same principle playing out in a chemical reaction.
Section 5. Concentration and titration. Applying the mole to solutions.
Out in the lab, chemists are constantly dissolving things into liquids to create solutions, so we absolutely need to know how to measure the mole in liquid form. Concentration simply tells us how much solute is dissolved in a specific volume of solution. You can express this in 2 main ways, either in grams per cubic decimeter, or, you guessed it, by using our trusty mole as moles per cubic decimeter, which we call molar concentration. But what if someone hands you a solution and you have no idea what its concentration is? Well, that's where you'd use volumetric analysis. Specifically, a really cool technique called titration. By carefully reacting a solution whose concentration you actually do know, called the titrant, with your mystery solution, you can use the reaction ratio to calculate the exact molar concentration of the unknown.
Section 6. Formulas, yield, and purity. The real-world laboratory checklist.
Now we're getting to the real-world laboratory checklist, where all these mole calculations truly prove their worth. First up, chemists actually use moles to discover the very formulas of unknown compounds. If you analyze a substance, you can figure out its empirical formula, which is just the simplest ratio of its atoms, in 3 foolproof steps. Step 1. Find the mass of the reactants taking part. Step 2. Convert those masses into moles to find your mole ratio. And finally, step 3. Write the formula out using that simplest mole ratio. Boom, you've got your empirical formula.
But here's the thing, that simplest ratio isn't always the true reality of the molecule. To find the real, full molecular formula, you take that empirical formula you just found and multiply it by a factor, which we represent with the letter n. How do you find n? You just take the true relative molecular mass of the substance and divide it by the mass of your simplified empirical formula. It literally scales it right up to the real molecule.
So the crucial takeaway here is that the mole gives us the mathematical tools to evaluate whether our chemical experiments were actually a success. We use this rapid-fire set of formulas. Percentage yield tells us how much product we actually got in the end, compared to the theoretical maximum we calculated we should have gotten. Percentage composition tells us the mass percentage of a specific element inside a compound. And percentage purity, that tells us how much of our sample is actually the pure substance we want versus just a bunch of useless impurities.
Which really brings us to this powerful thought from the text. The amount of a product formed in a reaction is always determined by the limiting reactant, determining the efficiency of chemical plants. It's honestly amazing when you zoom out and look at the big picture. We started today by trying to count completely invisible atoms. We learned how to bundle them up into a clever unit called the mole. And by mastering that invisible unit, we can scale all the way up to dictate the exact efficiency and success of massive, global chemical industries that produce the materials we rely on every single day. The invisible truly dictates the massive. It kind of makes you wonder, if you could somehow count all the microscopic atoms making up your own body right now, exactly how many moles of stardust would you be?